Okay, this is where we left off in class, everyone, with this question. The question of maximizing the area of this rectangle right here, okay? Maximizing the area of this rectangle, knowing that this rectangle is inscribed into this curve, y equals 16 minus x squared. And I think Alex added some context that this is 4, this is negative 4, this was 16, okay? And we left right when Fino was talking about calling this length x, calling this length L. Or I think y, I think you called it Fino, right? And what I said to you all as a class is if you make a equals LW, you change it to a equals x times y, I hope you see that this to this, not a whole lot of advance here in that all you did was just recalled length x and height y. The other more important thing is understand that when you look at a equals x times y, you really not added in the contextual constraint. So let's talk about that right now. The constraining detail that distinguishes this rectangle from all the rectangles in the Milky Way is the fact that this rectangle is inscribed or bounded by this curve y equals 16 minus x squared, right? Like, think about it, boys and girls. The fact that this rectangle has vertices, right, on the x-axis, upper vertices on the y-axis, that is the detail that makes it unique. Okay, that is what makes this rectangle unique. So how do we incorporate that detail, the fact that this rectangle has upper vertices on this parabola, how do we incorporate that detail into this area equals length times width? And this is what Jason started saying in class. He said, well, if I think about it, the way that I can incorporate the parabola into this rectangle is to make note to myself that this point right here, right, or we could use this point, but this point that falls on the rectangle's corner, right, and it also falls on the parabola. So that point, he said, let's just call that point, let's call this point right here, let's call this point here x comma y, okay? So now I'm going to be very careful and just erase kind of this x and y. All right, he's saying let's call, oops, I didn't want to do that. Let's call that point x comma y, all right? Now you have to be very careful. If that's the point x comma y, you can't forget where you're starting from here. This is the origin. If this is the point x comma y, x is this distance, y is this distance, right? So now what I can do is, well, if this is x, that means, like, if this is the x value, that means this dimension here is really 2x, because this is x, this whole length is just 2x. So now I get down to here, area equals 2x times y, okay? But even so, what's still not in here, if you look at this, everyone, what's still not incorporated into this equation is the fact that this rectangle's, really the dimensions are really controlled by the fact that these upper points right here are on the parabola y equals 16 minus x squared. I mean, you know, while we have kind of incorporated the detail that x and y is going to be coordinates of this point, thereby making this x and this y, we haven't incorporated the detail that this parabola is playing a very large role in determining the area of the rectangle, which is ultimately what we're optimizing. So the question is, how can I do that? Well, what's interesting is, if I think about it, this is the point x, let's call the point x, comma, if this is x, then this is going to be y, and y is just 16 minus x squared. Right? So because if y equals 16 minus x squared, this point right here will be the point x, comma, 16 minus x squared. And then if this is y, this is also 16 minus x squared. So at the end of the day, I now have area equals 2x times 16 minus x squared. And now if I look at this, this is still the area of a rectangle. But now what you have done is you've incorporated the particular details of the context that make this rectangle unique from all the other rectangles in the universe. Okay? So now at this point we are trying to, what are we trying to do now? Maximize the area of the rectangle. And here is where, if you look at this, right, if you look at how we're defining x, you can make some commonsensical domain restrictions. By logic, you know, x, it has to be bigger than 0, okay? But also x has to be less than 4, right? Because if this length is x, x can be 0 or it could be 4. Actually, no, x cannot be 0, x cannot be 4. So x is between 0 and 4. This is just kind of a logic check, right? Sometimes we think about the domain and ask ourselves, is there anything in this situation, in this context, that would allow me to make some commonsensical domain statements? And this one has yes. So now I'm going to go here and say, okay, a equals 32x minus 2x cubed, right? I'm trying to maximize area. At the very least, I have to work with a prime, or dA by dx, which equals 32 minus 6x squared. Okay, no points of non-differentiability. I'm going to go ahead and set this equal to 0, and I'm being very methodical as I look for first derivative critical points. When I set this equal to 0, I will get x equals the positive or negative root of 32/6. Mathematically, I do have those two values of x that make a prime equal to 0, but in the context of our problem, I just care about the positive, right? And 32 over 6, let's see, 32 divided by 6 is about 5. So you can make a, you know, if you want to, you can say this is about root 5, about root 5. The point is, I'm doing this mental math to show that this number is within my domain here. And again, once again, one critical point. Let's see, I'm looking here at a prime, and I'm choosing between a first derivative test for extrema versus a second derivative test for extrema, and I'm going second. A double is going to equal negative 12x, okay? And a double at my critical point, which is the square root of 32 over 6, it is going to be negative. So I have a point at x equals radical 32 over 6, a prime equals 0, and a double is negative, which means the a function is concave down. So by the second deriv test for extrema, comma, area is maximized at x equals the root of 32 over 6. Now we've done the calculus. Now we go back and we make sure we answer the question. The question is asking, what are the dimensions of the one with largest area? Okay, so I haven't answered that question yet. So if x is radical 32 over 6, the rectangle's dimensions will be, let's see, we said this dimension is 2x, so it's 2 times radical 32 over 6. It's that number by, what's this dimension? It's 16 minus x squared. So I'm going to say 2 by 16 minus 32 over 6. Those are the dimensions. Hey, come on in, Connor. Those are your dimensions of the rectangle with max area. Yeah, you can speak. Can
I get my quiz?
Oh, yes. Okay, sorry. You just caught me in mid-swallow. I was drinking some water. Okay, so that you now have a sense of optimization. Now, if you open your book to page 284, okay, you will see that, oh my goodness, optimization questions, they vary. I mean, there's no way one can cover every possible optimization question. But the most important thing is to understand the larger story. What is being optimized? What are the constraints? Can I incorporate the constraints? And then once you have, and then are there any kind of common sense domain restrictions? And then the calculus begins, okay? So what I'm going to have you do here is try this one. Okay, are you ready? Let's try page 285, and let's try question number 37. Okay? And you can go ahead and replay me if you need a little hint. You can stop along the way. All that is fair game. Okay, 37. Oh, I'm actually going to pause. Whoops, sorry. Okay, so the first thing I want to show you, and I bet you there's a bunch of you who looked up, how do you find the surface area and the volume of a cone again? What's the formulas? But anyway, what you're minimizing here is the surface area of the cone, but not including the circular base. And that's called the lateral area, in case you're curious. So I'm minimizing the lateral area, okay? And I just wrote here surface area minus area of the circular base. The lateral area of a cone is pi RL. RL is the slant height of the cone, all right? And I want to talk you through where you probably got yourself a little stuck now here. So lateral area equals pi RL. The constraint is volume equals 100. So 100 equals 1/3 pi r squared h, right? And this is, and again, you probably looked up the volume of a cone. So here's the contextual constraint. And the question is, how do I incorporate this constraint into here? And the first thing you're probably noticing is, I have R and H involved in my constraint, but I have R and L. What do I do? Like, because if I solve here for H, I have no H in this equation, right? If I solve here for R and then substitute back in, I'll be left with L and H still in the equation to be optimized. Do you understand, right? So the fact that I have my equation to be optimized and my constraint here, regardless of which variable I solve for in my constraint to sub back in, I'm still left with two independent variables, which is doable, but the question is, can I make my life easier? You know, can I take a look at this problem and say, is there something else that I could do? And there's something else, yes, there is. If you look at slant height H and R in a cone, you know that R squared plus H squared has to equal L squared, okay? And what I did here was, well, I then looked at my equation to be optimized, and I solved R squared plus H squared equals L squared for L, and I put L in terms of R and H into the equation to be optimized. And now my I is here, okay? Now you're looking at the equation to be optimized, and I'm now back at the constraint. And what I like about the equation to be optimized now and the constraint is that now they both have the same independent variables, which would then allow me to solve the constraining equation for one of the variables and then sub back in. Looking at what I have to work with here, I am going to argue that I'm going to use some savvy algebra to make my life easier. I'm going to argue that solving for H, okay, and then inputting here and squaring it will bring us closer to the equation where the calculus is going to work easily, most easily. Do that part with me and then meet me. Okay? L will equal pi r times the square root of r squared plus, now here's what's H going to be. It's going to be 300 over pi r squared, all of that squared. You agree? Okay? All right, now I'm going to go over here and do L equals pi r times the square root of r squared plus 9,000 all over pi squared r to the fourth. Okay? All right, here's a little trick for you. I can go ahead and take the derivative now. I could find L prime, right? I have L as a function of one variable. I'm ready to go. Oh, I should also say that in this case, we know the radius has to always be positive, right? Okay, I'm ready to go. But if I took the derivative now, I've got to use the product rule. I have to use the product rule. Don't really want to use a product rule. So you know what I'm going to do? I'm going to take the r and put the r back into the radical. So if r out of the radical is r, If I put back r into the radical, in the radicand, I will have r squared. In other words, I have this. L equals pi times the square root of r squared times r squared plus 9,000 over pi squared r to the fourth. Okay? See how I did that? And then I'm going to distribute. L equals pi times the square root of r to the fourth plus 9,000 over pi squared r to the negative second. Look what I did here, right? All I did was I wanted to make a mental note that I know 9,000 over pi squared, this is just a constant. It's just a number. It's not a particularly pretty number, not to be judgmental, but it's just a number, okay? And now I'm going to go ahead and minimize, take the derivative and do the calculus now. But guess what? I have another helpful hint to you. L equals some number times the square root of this, okay? Would you agree that, let's walk over here. If I have y equals the square root of something, and y is smallest, would you agree or not? Y is going to be smallest when the radicand is smallest. In other words, if I'm trying to find when y will be as small as possible, won't y being as small as possible occur when the square root of box, when box is small as possible, right? If box is small as possible, then certainly the square root of it will be as small as possible, and y will be as small as possible. So really, I'm going to make a note to myself and say L will be minimized when the radicand is minimized. Right? So I'm just going to minimize. I'm going to find when the radicand is minimized. So I'm going to minimize the radicand. What's the radicand? I'll call it R. Oh, I can't call it R. I have a little r here. Let's call it the radicand. Let's call it capital R. Okay? The radicand is r to the fourth plus 9,000 over pi squared r to the negative second. Now, look at this, boys and girls. Do you see? There is no calculus involved yet. Nothing. All we're doing is setting up ourselves to do the calculus in the way that's going to be the most sane. The most sane. Okay? So the point here is I'm going to minimize the radicand. If I minimize the radicand, then I will be minimizing L, which is the lateral area. And now I am good to go. And I'm remembering R is positive. Okay? So R prime equals 4R cubed minus, let's see, is that going to be 180,000 minus 180,000 over pi squared r to the negative third, right? And I'm, a big fan of using factoring when I can. Oh, no, or maybe not. It's up to you. Okay, we know here there's a point of non-differentiability. R can't equal 0, okay? R can equal 0. This is 1 over r cubed. I actually am going to factor. I'm going to factor out 4r to the negative third. Remember this trick? This leaves me with r to the sixth minus 4 into 180. What does that become? 4 into 45,000 over pi squared. Right? Yes, I love that. Okay, so here is r prime unfactored. Here's r prime factored. We know here that r cannot equal 0. And the other critical point we're seeing, when will r prime equal 0? When this factor equals 0. So r to the sixth minus 45,000 all over pi squared will equal 0. At the end of the day, r is going to equal the 6th root of 45,000 all over pi squared. Now already I found one critical point, and if you're wondering, yeah, well, these applied optimization questions, will there always be one critical point? I'll tell you this, I never hide anything from you. On these applied absolute max and min questions, there are often, many times, there is only one critical point, and that should make you happy. Okay. I have to show that this is going to be a min. All right. First or second derivative test for extrema. Oh my gosh. I hope not a single one of you is raising your hand saying, first derivative test for extrema. Why on earth would you want to figure out numbers to the left and right of this? No. Plus, look at the first derivative. Second derivative is going to be such an easy peasy piece of cake. So r double is going to equal 12r squared. Oh, my goodness. How offensive. 12r squared plus, okay, some big number, some huge number divided by pi squared, r to the negative 4th. And if I look at this, for all values of r that are positive, right, positive number, this is always concave up. And when I say this is always concave up, the r function is always concave up. So, by second derivative test for extrema, comma, r and then lateral area, frankly, and the lateral area of the cone are minimized when the radius equals the 6th root of 45,000 divided by pi squared. See? Are you all kind of figuring out here that second derivative test can be your best friend? I hope you are. All right? Okay, I am going to put up homework right now. See, I know you're all looking at this little clock here. You're going to give me grief for saying, yeah, the screencast was too long. But oh, hush, hush, children, hush. Okay, there it is, homework right here. All right, please work together, definitely work together. And what I may do over the weekend is I may put up solutions to these, okay, and via screencast. So wait for those. I'm not promising that, but I might if I remember. But otherwise, we'll go over these in class. All right? All right, everyone, look at your calculus. You can't neglect the calculus baby. You just can't, right? You've got to look over your stuff. Keep on top of everything, keep the whole picture in view. And with that, I bid you a wonderful weekend.